Hello everyone, we are Group 3 and today we are presenting on Chapter 4 Web Services. I am Chandrika Tituli and with me are Humaira Mahmood Badhun and Nisha Tasmin. Now let's begin the presentation. On slide 2, here is the overview of what we will discuss today. We will look at how the web services evolved and how the web services in this slide we can see that how the web services are generated by the web server and with assisted by the several network components. And let's move to slide 3, evolution and design of web services. Initially, web applications were built using monolithic architecture where everything was developed together in a single system. However, as the internet evolved and companies needed to integrate with other platforms, APIs became popular. Later, with the rise of mobile applications, APIs became even more important, so multiple devices could use the same backend. This led us to monolithic approach. Now let's go to the slide 4. Monolithic approach. The monolithic approach means the whole application is developed as one big unit. The presentation layer and the business logic stay in a single code base. It is usually built using MVC framework like Spring MVC, Symfony, or Rails. For example, a hotel booking website where all features like searching and booking are handled together. And let's look at the pros and cons. Faster benefits, faster to build and release, especially when creating a minimum viable product. Simpler design and fewer components, API development can be postponed until it's needed. Drawback, hard to scale. Many developers editing the same code base leads to complexity, eventually requires rewriting or major refactoring. To solve this, we move to a better model than slide 6, API first approach. The API first approach means we design and define the API first before building the client. This prevents duplicate logic across different platforms like mobile apps, websites, or partner systems. Let's now see how this helps structuring API. Here, all clients communicate through one shared API. This gives several advantages like less duplicate code, easy maintenance, better scalability, and clean separation between the client and server logic. Now,
Now let's talk about pragmatic approach. It means focusing on practical, efficient solutions that work in real-world scenarios. Let's make it a bit clearer with this figure. In this figure, represents a pragmatic analysis of web service discovery models and architecture from a qualitative perspective. On the left side, under data process, information from the internet such as WSDL files and tags are collected. These files describe web services in terms of content, type, messages, port, name, and tag. All this metadata is then processed and passed through a clustering algorithm called WT class, which help organize similar services together. On the right side, in service discovery, users send a query to the web service search engine, which looks through the clustered data and returns a response with the most relevant service result. Now, let's talk about types of web services. We see here there are two types of web services, function-centric web service and resource-centric web service. Let's talk about function-centric web service. The function-centric web services are designed around the specific task rather than the focusing on data or resource. There are many technologies like Corba, XML, RPC, DCOM, and so among them, SOAP become the dominant technology. So here I will discuss about Simple Object Access Protocol SOAP. It uses XML-based message to exchange data between client and server. The client sends a SOAP request message that contains details about the operation. This request goes through a SOAP protocol over HTTP to the web service provider, which processes the request and returns a SOAP response in XML format. The entire communication is platform independent, secure, and follows a WSDL files that defines what each function does.
Then comes the resource-centric approach. This is a service of collected resources, and here we deal with create, read, update, etc. CRUD operations. So one of the prominent functions of resource-centric is REST. So what is REST? REST means representational state transfer. So a resource-oriented structural style is applied for the APIs. The key concern here is the simplicity and lightweight development of this model. So the REST does some vital operations including the playlists per se. So here we have given one example of the playlist. So when it is only on the playlist URL, it's a collection of playlists. So there is no classification per se. But then when we go to another URL //123, it's a specific one. Again, if we add /songs, this is a specific song inside that playlist earlier we mentioned. So it works on unicity of the URLs and on HTTP methods.
To scale web services, we generally use two techniques: divide services into functional parts, and the other one is adding more clone duplicate servers. REST web servers support both, making scaling flexible. Now let's see how stateless design helps. In scalable systems, service machines should be stateless. This means they don't store any user session data internally. All state is stored in external systems like databases, cache, or queues. This helps with load balancing, easy maintenance, and adding new servers whenever needed. Going to slide 15, um, handling state and persistence. Only temporary cached data should be stored locally in on-service machines. This ensures no data is lost if a machine fails and systems remain consistent. Authentication tokens are one common example handled externally.
Now, let's talk about authorization and resource locking in stateless web service. So here, in this figure, we can see how a stateless web server handles authorization using a shared object cache. When a client sends a request with an authorization token, the web service checks the cache for that token info. If it's found, alright, access is granted instantly. If not, it's rebuilt from the main data store and then stored in the cache for the next time. This keeps the service fast and still stateless. Another challenge is resource locking. To manage that system, often use distributed locks like Zookeeper or even avoid the locks by optimistic concurrency or message queues to stay scalable.
If there is any failure to prepare the phrase, then what happens? So it actually applies for the synchronous objectives. That is, when there are multiple operations one dependent on other, and there is a serial execution, then uh, the prior one is fully dependent on the post one. So what happens if the earlier one fails? The later one will be automatically know about it. So what's the solution? The solution is to roll back. So the whole system is aborted and back to the first approach. So that's potentially the avoid avoidance of error. However, we need to do it more efficiently. So whenever, as we see from figure 4.8, the error happens in fulfillment service stage, then it doesn't roll back to the client or service. Rather, it returns to the payment service, that is the immediate prior one, so that there is efficiency and at the same time the solution.
Caching in REST devices. Caching helps the web services handle more requests efficiently and uh, reduces the backend load by serving immediately uh, with the stored data built on top of HTTP caching principles, especially useful for REST services or high traffic when there are many requests or loads that have to be served. And role of HTTP caching. REST services use get, post, put, delete, and GET requests are cacheable and read-only, where no updates are done in the database. Enables clients or proxies to serve stored data quickly, makes REST systems faster and more scalable. And the challenges are local machine caches can hold different versions of the same data, which leads to inconsistency. Updates in one cache may not reflect in others, and coordination between multiple service nodes become difficult. And authentication, open return the user specific data, use HTTP headers to create separate cache, ensures correct isolated data for each authenticated client. Mm, Best practices for caching: make resource public whenever possible, and reduces the database hits and the server load. Get requests, its importance, must not modify the data and never causes database updates or side effects. And using get for actions like unsubscribe or delete is incorrect and breaks REST principles. Changes should use post, put, or delete instead. Now on the slide 22, reverse proxies such as Nginx and Varnish help serve cached responses quickly and greatly improves the response times and reduces backend strains. And scaling with reverse proxies and load balancers. Combine caching with load balancing for better scalability. And together they ensure and together reverse proxy and load balancer, they ensure the fast, reliable, and scalable. Load balancer mainly manages the traffic and replaces failed servers automatically.
Now let's talk about functional partitioning. But before understanding the need for functional partitioning, let's look at the problem with having a single large web service. When all features are packed into one service, it becomes hard to scale and difficult to maintain and even risky. Because if one module fails, then the entire system can go down. Deployment take longer and even small updates can affect unrelated parts of the code. To fix this, we use functional partitioning.
Now move on to the details about functional partition. It is a, it is happens through functional split. So when there are multiple functions in a single task, then they are divided based on their operations. Per se here, the main server is divided based on the product catalog service and user profile service. So when they are divided, the product catalog service, this is itself divided into multiple servers from 1, 2, 3, etc. So these servers each does a specific part of this. Similarly, the user profile service does separate tasks for each. Finally, they all are stored in their respective databases. That's all from us. Thanks for being with us.